Hi, in previous lecture I discussed Prim's algorithm where at every iteration we are adding one adjacent edge to the subgraph having minimum weight and not creating any cycle. In today's lecture I will discuss Kruskal algorithm. It was developed by Joseph Kruskal who was a second year student at that time. So according to his name the algorithm name is Kruskal algorithm. It will create a minimum spanning tree of a weighted connected graph G equals to V for vertices, E for edges as an acyclic subgraph with number of vertices minus 1 edges for which the sum of edge weight is the smallest. So it will create a minimum spanning tree where sum of all weights should be smallest and it should be acyclic. In Prim's algorithm, during the process of creating minimum spanning tree, every time it is connected, but in Kruskal, it is not connected. You can say it is a forest, and when the final tree will be created, we can say it is a tree. So the minimum spanning tree is always acyclic but not necessarily connected on the intermediate stages of the algorithm. Finally, it is connected, but in the intermediate process, it is not connected. While in Prim's algorithm, it is always connected as we are choosing a adjacent edges. So the algorithm first sort all the edges in increasing order. Then every time it will choose one edge if it is not creating any cycle. And if it is creating any cycle, it will simply skip it and move to the other edge. Let's discuss the algorithm. Input is a graph and output is a minimum spanning tree. First step will sort all the edges according to their weight. In case of Prim's algorithm, starting one vertex was given, means one start vertex was given, then from that vertex we'll create the tree, while in Kruskal it is empty. No vertex, no edge are given. The minimum edge will choose as the first edge. Encounter equals to 0, k equals to 0. So encounter initialize the set of tree edges and its size, while k initialize the number of processed edge, how many edge we already processed. While encounter less than number of vertices minus 1, do k will be k plus 1. Then if et edges in spanning tree union ek is acyclic, means it is not creating any cycle, then et will be et union ek, so we'll add that edge, and encounter will be encounter plus 1, next return et, so finally it will return the spanning tree. Here main operation is this union. Every time we are adding the minimum edge. So with the efficient union find algorithm, the running time of Kruskal algorithm will be dominated. So what is the running time here? It's order of number of edges log number of edges. And this number of edges is always less than number of vertices square. So we can write log A equals to order of log B, when this number of edges is less than number of vertices square. So we can rewrite order of number of edges log number of vertices. In case of Prim's algorithm, if the edges are not sorted, then running time is theta of number of vertices square. If we are using a min heap for edges, then running time will be theta of number of edges log number of vertices. And in case of Kruskal, it is theta of number of edges log number of vertices. If log E written, that also fine, or log V. So both are Kruskal running time. Let's discuss one example of minimum spanning tree by using Kruskal algorithm. Here shaded edges belongs to the forest. We are saying forest as it is not connected, and the algorithm consider each edge in sorted order by weight, and every time the pointed arrow is the edge what we are considering. So sorted weight of the edges are 1, 2, 2, 4, 4, 6, 7, 7, 8, 8, 9, 10, 11, 14. I'm using the same graph that I used for Prim's algorithm. So first minimum is 1. We'll consider 1. Next minimum is 2. CI and GF. We can choose any one. Let me consider CI. Next minimum is this 2. So we'll include GF. Next minimum is 4. There are 2 for this one and this one. So let me include A, B. Next we'll consider CF. After 4 it's 6. If we'll include this 6, then it will be a cycle. So we'll skip 6. After 6, 7, we can include this CD. Next another 7. If we'll include this in this spanning tree, then it will be a cycle. So we'll skip it. Next is 8. We can include AH. Next is another 8. BC. If we'll include BC, then it will be a cycle. So we'll skip it. Next is 9. DE. We can include DE. Next is 10. EF, but if we'll include EF, it will be a cycle. So we'll skip it. Next 11 BH, it will be a cycle, so we'll skip it. Next is 14 DF. If we'll include it, it will be a cycle, so we'll skip it. Or you can simply stop when number of edges equals to number of vertices minus 1. So this is the minimum spanning tree we found by Kruskal algorithm. Every time we include one edges from the sorted list, if it is creating a cycle, we are skipping it. If it is acyclic, then we are including. And finally, we'll get the minimum spanning. With this, I am finishing Kruskal algorithm. In next lecture, I will discuss one example in both Prim's versus Kruskal algorithm. If this lecture is helpful for you, please like and subscribe. Thank you.